So Summit is designed as an open source Python package for reaction optimization. And we designed it because we saw in the literature that there's lots of examples of people using machine learning type techniques to optimize chemical reactions. Yet there's not standard comparisons on the same reactions with the same number of repeats and the same algorithms. So therefore, we created benchmarks, which are simulations of chemical reactions that we can run multiple times in the computer. So we get repeatable experiments. And we have this reusable software with several different strategies implemented. So we can compare different machine learning optimization strategies on our in silico benchmarks. We have these strategies available already, and there's actually more that have been added since the original publication. So you always keep looking at the repository and you'll see as we update things. And the benchmarks, these are just a couple of the ones we have. There's two types. One are mechanistically based benchmarks where we've taken a kinetic model, written out the differential equations, and then we basically every time you run the reaction virtually, you say what the conditions are and the residence time or reaction time. We integrate from the initial conditions over the reaction time to get our outputs such as yield, or if it's a continuous reaction, space-time yield. And you can see here in this optimization problem, in this benchmark, we have several variables: temperature, residence time, the concentrations, and the equivalents. And then it's a multi-objective problem, so we can optimize both. We're trying to optimize both the amount of product coming out per unit time, as well as minimize waste. And so we'll see in a minute how Summit can handle these multi-objective problems. And we also have the CN cross-coupling benchmark, which shows that Summit can handle both categorical and continuous variables. So categorical variables are things like catalyst and bases where we have to make a choice. Continuous variables are on a number scale, so things like temperature and time. Here's just an example of what we can do with Summit. This is with that first benchmark, the nucleophilic aromatic substitution reaction. And you can see that we actually are able to compare different strategies. And in this case, since it's multi-objective, we're comparing something called the hypervolume that measures how well we're operating or finding the optimal trade-offs. And you can see that there's this Bayesian optimization strategy called TSEMO that performs very well. So in terms of the way Summit works and what we're going to be looking at, there's these two key pieces: the strategies, which is the machine learning algorithms, and they all have the same application programming interface or API, so you can switch them out easily. And those give suggestions for conditions, reaction conditions that are run by a benchmark. So we'll look at both benchmarks that are already implemented as well as building our own benchmark. And when we feed back the results from the virtual experiments run by the benchmark, we can then use the strategies to suggest better experiments based on what we've already seen in the lab, but in this case, our virtual lab. And we'll use this thing called Runner, which puts it all together that allows us to do closed loop optimization, as well as has some nice features around logging. Okay, and so this is exactly what we're going to be looking at. We'll set up a benchmark, we'll set up a strategy, and then we'll put it all together with runners. So let's go ahead and get started. I've got the tutorial up here, and I'll just note a couple things. First, what you want to do is you want to go ahead and install Summit. And so this is running in Google Colab. So that's the way we're going to do it. We're going to do it directly in the notebook. I've already installed this previously, so everything installs pretty quickly. But if you run this for the first time, it might take a couple minutes. If you're running on Jupyter Lab or Jupyter Notebook or just in a regular Python script, then you would run this from the command line as usual. I'll also make some other notes. Go check out our GitHub page. So that has our all of the code, and will give you the most recent updates we've done, including new releases. There's also the documentation, which has more detail on everything we're going to talk about today, including detailed examples and code that you can run yourself to try all the techniques we'll look at. So I encourage you to go look at the documentation if you want to know more about anything we talk about today. So as an outline for the tutorial, we'll break it into 3 parts. In part 1, we will use strategies to optimize this nucleophilic aromatic substitution benchmark that I showed in the slides, and I'll show again in a minute. And part two, we'll then build our own benchmark based on solely experimental data. So instead of using a mechanistic model, we can just use data and train a machine learning model in 2 lines of code that we can then use as a benchmark for testing different optimization strategies. So if we have a new type of problem and we have some experimental data, we can build a benchmark to see how different optimization strategies would perform in the future. And finally, we'll optimize this newly created benchmark and talk a little bit about how the sort of machine learning strategies compare to classical design of experiments. Okay, so now that we've got everything installed, let's go ahead and start on part one. What I've got here is a figure reproduced from this paper from Richard Bourne's group at Leeds, where they were basically building a kinetic model of this nucleophilic aromatic substitution. And they figured out what these parameters are, these K parameters, from experiments. So we can just use this model as a representation of what would happen in the lab. And so, as I said earlier, in the benchmark, in the code, you could go look at it here in the docs, but we won't go into detail on the differential equations. The main thing to know is that every time we put in conditions, these differential equations will be integrated to find where our outputs are. So the way we set up a benchmark is we'll first import everything we need. We can just import from star. And I know if you're a Python programmer, that might make you uncomfortable, but don't worry, I've made sure everything are only the things that we need are being imported. And the way we can see the benchmark and understand what the optimization problem is we call the name of the benchmark. All of this is in the docs here. And then also we can ask for the domain. And if you've ever used a Jupyter Notebook before, you know that you can either press this play button or type Shift Enter to run a command or run a cell, excuse me, with some code. And if you put whatever variable you put at the end of the cell will be printed out afterwards. So we've asked to print out the domain. So let's take a look at what this is. It's got 4 parameters that we can vary. So the residence time, tau, the equivalence of pyrrolidine, that's compound 2 up here. We have the concentration of difluoronitrobenzene and the temperature of the reaction. So those are the 4 parameters we can vary, and they're all continuous parameters, and these are the bounds on them. So the optimization strategies will take those into account. And then we have the space-time yield, which is the amount of product we're making per unit time that we're trying to maximize. So we're trying to maximize the amount of product we make and minimize the E factor. And the E factor is just the ratio of waste produced to product made. So we want to minimize that. And if you want to read more about how domains are set up and what the different functions are, you can read the documentation here. But we'll also go through an example in a couple minutes. So let's go ahead and create some test conditions. So the way we'll do this is we'll use something called a data set, which is an extension of pandas data frames. If you've ever used those in Python, they're basically like spreadsheets, but very efficient spreadsheets. And what we can do is we can just specify a dictionary with some different values. You see I'm looking over at my other screen just because I have these values already written down that are going to be the conditions at which our reaction is run virtually. And you'll also see that I'm typing an extra parameter in this tuple for each column or each variable. And that is to say that the column is a data column versus what we call a metadata column. So there's an extra feature in data sets on top of regular pandas data frames that allows you to specify certain columns as metadata columns. So I'll do that right now. And what that allows us to do is have certain columns only pass through the algorithms, but not actually used in any of the calculations. And therefore, we can keep information about maybe the way the experiments were run or any information about what the strategy used to make its decision about what the next experiment should be. That can be incorporated into the data set without affecting the calculations. So here you can see I've got this conditions data set, and it prints out exactly like a data frame would in pandas in Jupyter. But if I want to just see the data columns, I can click here, I can type data columns, and I'll see that only these 4 are the data columns. And then if I add meta in front, I'll see that the strategy is my metadata column. So this is a nice feature for keeping any extra information around. So now let's use that benchmark from earlier and actually run these conditions just to see how this works before we do any optimization. So you can see now we have some extra columns, the space-time yield, the E factor, etc. And in particular, I'll note that these are quite high. So space-time, or excuse me, the E factor is quite high. We'd want this 10 or lower for the pharmaceutical industry, for example. And the space-time yield is quite low. If you know anything about this reaction, we'd want it to be an order of magnitude higher. So then the question is, can we use optimization to do that? Can we try to find some better conditions? And that's where Summit comes in and some of the strategies that we already have. So let's start with a very, very simple strategy, a random strategy. Now, this obviously is probably not ideal, but you'd be surprised how well it works sometimes. And what we always need to do if we're running this in a Jupyter notebook and we run some experiments just to test things out, before we run a test of the optimization, we need to reset the benchmark so that we're not keeping around these conditions we've run so far, because the benchmark will keep track of every time we say run experiments. So we can do this by creating a strategy called random, or instantiating a strategy, better put, and we just pass in the domain. And as you remember, we can just call .domain on the benchmark to get the domain for this nucleophilic aromatic substitution. So that specifies, again, what the parameters we can change are and the things we're trying to optimize. And now, if you remember earlier, we said that we're going to take the benchmark. We're going to combine that with a strategy, and the runner will do all the work of making these work together. So that's exactly what we do. We just say strategy equals strategy, experiment equals snar benchmark. And let's say we want to run for a maximum of 100 experiments. It's quite a lot, but we'll do that. And we'll say r.run to run this in closed loop. So it's actually going, and every time the strategy is suggesting an experiment, the benchmark is running it, and then we're going back and asking the strategy for more experiments, and the benchmark's running it. Let's visualize what happened. So the way we can do that is there's a method in the benchmark called Pareto plot, which is really useful for multi-objective problems. So it shows both objectives on the same plot. And you can see, actually, we got pretty lucky here this time. We got some pretty high space-time yields, but you can see a lot of them are quite low. And the thing I'd note here is, if we've run this once and we happen to get very high space-time yields, but we could run this again, and if you run this a couple of times yourself, you'll see that you get completely different results each time. So random strategies work quite well in the limit of large numbers of experiments, but when we have a small number of experiments and we want to quickly try to find the best conditions, we want to turn to some other strategies that might work better. So let's do that. Let's look at something called Bayesian optimization. And as before, we're going to start by resetting our benchmark. And Bayesian optimization, I think you've heard in other parts of the conference, but the basic idea is that we are using a model to represent our reaction. So the model represents the relationship between the inputs and the outputs. And then we optimize that model, because now we have something that's cheap to evaluate, to find what should be our next conditions. And we don't exactly optimize the model. We actually optimize something on top of it that gives us a balance of exploration and exploitation. So finding new conditions that we haven't looked at before, as well as exploiting and trying to just maximize near what the best points have been. And so that's called an acquisition function. So what we need to do, we want to use the Bayesian optimization strategy. And the one we'll use here is something called STBO. And again, you can always see a list of all the strategies we have in documentation. But you'll start to see that all of them work exactly the same. We pass in the domain, and then we use the runner. And we say the experiment we're running is this benchmark, the start benchmark. And let's say maximum of 20 experiments. So now let's run it. And what happens? Ooh, we get an error. So what this is saying is that we must specify an objective when using a multi-output model. And if we remember correctly, this is a multi-objective problem. If I scroll back up here and show you the domain, remember we had two objectives. One was maximizing space-time yield, and the other was minimizing E-factor. So the problem is that this strategy is really only meant to work with one objective when we have one thing we're trying to maximize or minimize. So we need some way of converting our multi-objective problem into a single objective problem so this benchmark can use it. And the way we'll do that is we'll use a nice feature of Summit called transform. So in particular, there's one called multi to single objective that does exactly what it says on the tin. It converts a multi-objective problem into a single objective problem. And we have several of these types of transforms, but this particular one just allows you to suggest an expression that will be used to convert your multiple objectives into a scalar value. So the way it works is you just specify the names of the objectives and any sort of algebraic manipulations of them. And then that will become what the objective is for the problem. In this case, you can see I've put a negative in terms of space in front of space-time yield because we want to, that's a maximization and the E factor is minimization. So we have to choose to negate one of them and make either the whole problem minimization or the whole problem maximization. In this case, I've chosen to make the whole problem a minimization problem. And so therefore, I'm just going to say maximize equals false. So now, if I pass in this transform into the strategy, now every time that I ask for some new experiments from the strategy, the CBO strategy, then underneath the hood, my data will be, the objective values will be converted by this expression into a single scalar so that it can be used with this Bayesian optimization strategy. And we'll go ahead and run it, but just before that, let's just set up the plot that we'll want this exactly the same as before. So we have our benchmark and we just say Pareto plot and color bar equals true. So now you can see, oh, oops. I'm going to stop that. I actually want this to only run for about 20 iterations. So you can see it takes a bit longer because it's having to train a model each time and optimize the acquisition function, but it's still pretty fast. This is using GPyTorch. So you can see in a small number of experiments, we got pretty good conditions. And this was without, was running only 20 experiments. And so this is the nice factor of using an optimization strategy is we can run a small number of experiments and get pretty high values very quickly. And I'll note that this is actually not the best multi-objective strategy that's available in Summit. So if you want to see one that performs better, I use TS-EMO, which is actually a native multi-objective strategy. So you can remove this transform and then automatically just start running it. But you'll see it takes quite a bit of time. It does a little bit more computation to get experimental suggestions. So in this case, I'm going to stop this and let you run this on your own time if you're interested, just to see the performance. So let's just go back and rerun this Bayesian optimization strategy. I've got my transform. And it will run. And what I want to do is I actually want to compare what we had initially is just our nominal conditions that we ran above to what the best conditions are when we use the Bayesian optimization strategy. And the way we can do that is if we call this benchmark and ask for Pareto data. That means the best conditions that trade off maximizing space-time yield and minimizing E factor. You can see we get these here that tell us, okay, these are the actual concentrations and residence times that will work best for you. I think I forgot to actually name this initial conditions up here. So, or conditions, excuse me. Was what that was named. So you can see that these are slightly different than what our initial conditions were. And so significantly higher temperature, et cetera, to get better space-time yields. So this is one of the nice features is we can, even without having a lot of knowledge about the reaction initially, can quickly optimize and find better conditions. Okay, so I've shown you in the first part how we can combine strategies and benchmarks and quickly switch out different strategies with the same benchmark to compare how they perform. So now let's see how if you have a new type of problem, maybe a new type of reaction you want to look at, and maybe have a little bit of data that is already around, you can see how different strategies would perform on that type of problem. And so I think this is really useful before you go in the lab. You can get a sense of, okay, what type of strategies will work, and just kind of assure yourself that this is the right approach for you. So what we'll look at to do this is we're going to look at some data from a paper from Klaus Jensen's group by Brendan Reisman. And the paper has a bunch of data from Suzuki coupling reactions where they're varying not only the temperature and residence time and catalyst loading, but actually the catalyst and base they're using. So this is interesting because it's not only varying continuous variables, but also categorical variables. And so this presents a unique challenge because we need to, when categorical variables are things where we're choosing something. So we're choosing which catalyst we're going to use, or we're choosing which base we're going to use. So Summit can do this, which is sort of distinct from many other optimization packages. So we'll import what we need. It's actually pretty similar to what we had above, and this is just some extra functions to help us with importing the data we'll need. So the first thing we're going to do is get the data. And actually, normally you would maybe just have a CSV or an Excel file on your computer. But to do this, I'm actually just going to copy this line in. We'll use some data that's already available in Summit in a CSV. So the way we do this is we say dataset read CSV. Very familiar probably if you've ever used pandas, and I'll just copy this in here to make sure I'm consistent. So we'll read in the data set from the CSV, and I'm just going to do one thing that is a sort of problem you should note just for the future, and I think we'll make sure that the package sort of helps you and doesn't allow you to do this in the future. But the yield, if you name something a variable yield, it will cause problems, particularly if you use that multi to single objective transform I talked about previously, because yield is a keyword in Python. So it's actually a reserved phrase for when you're doing like asynchronous tasks. And therefore, you really don't want to be using your variable names as yield. And so therefore, we should use something like YLD as an alternative. So I've just renamed that there. And how about we print out the number of reactions we have? And just show the first couple reactions from this data set. Oops, I forgot a capital there. So, okay, so we can see we've got 96 reactions, and there's several different variables. So catalyst, the residence time, the temperature, the catalyst loading, and then we're optimizing the turnover number and the yield. And I forgot to say DS equals, so that didn't get renamed. So, okay, now it's renamed properly. And for the sake of time, I'm not going to do this plot manually here. I think that's something that's probably just matplotlib. So you can look this up on your own if you want to learn how to do these type of plots. But this just shows you the distribution of ton and yield. And what I'll note is if you look at, for example, if you go download a bunch of data from Reaxys for reactions, and which is a large database of papers and patents, you'll see that the distribution of these numbers over the course of thousands of papers looks very different from what we see here. Often it's very upward sloping. There's lots of high yields and very few low yields. And what's the benefit of these type of data sets is we get more the distribution, which probably looks more like what you would see if you plotted data from lab notebooks, where there's lots of reactions that give low yield. And we actually need those to make the best models we can. So with that side note, let's go ahead and set up the problem. And what we'll need to do is two things. So we'll need to first create a domain. So that's, as we talked about earlier, that specifies what parameters we can change and what we're trying to optimize. And then we'll go through and train the emulator. So let's do this. So the way we specify the domain is we actually add in variables to the domain. So you can see I've called domain here. And one of the nice is sort of, you can imagine, is that I'm just throwing the variables in and it will keep adding them to the domain. So I can use this plus equals syntax. So the first one is the catalyst, if you remember correctly, if you remember here. So the catalyst is a categorical variable. And so we need to use this categorical variable option. And I'll just say it's the catalyst for the Suzuki reaction. And levels is something that you should note. This is all of the potential values that the categorical variable can take on. So I'll just use a function from pandas that allows us to quickly get those. So all the unique values. So if I do this real quick, I forgot my comma here. I forgot to import pandas up here. Sorry about that. Okay, so now we've got that. Let's go ahead and add in some other variables. So the continuous variables. So remember the next variable was the resonance time. So remember the names need to match the names in the CSV file. That's something important to note. And I always I've made it required that you have to add in a description. So it would be ideal if you add in, for example, the units for people in the future. And for continuous variables, if you remember from earlier, we always saw that there were bounds. So here we can set the bounds on the variables. And just to make things quicker, I'm just going to copy in the rest of these. And then we also will do objectives. And the objectives are they work exactly the same as the parameters that we can change, except that you'll see that we use this option is objective equals true. So by default, this is false. So that's why we don't need it for these other ones. But if we set it to true, then someone will know that this is something we're trying to minimize or maximize. And then we say whether we're maximizing or minimizing. In this case, we're maximizing the yield and the turnover number. So now let's create our benchmark that represents this reaction. And the way we do that is we use a class called experimental emulator. And the experimental emulator is sort of an auto machine learning feature in Summit that can automatically look at your data, train a good model that will represent the data, and incorporate that as a benchmark. So it works with the same API as all the other benchmarks. So this is really nice because it sort of abstracts away all the details of train test splitting and cross-validation and such. So that's how we set up the emulator. And then I can just do train max epochs So if you've ever done any, machine learning or work with deep learning, you'll know about epochs. Here, this is actually training a neural network underneath using Scorch and PyTorch. And so 1,000 epochs is usually about right for this size network and this amount of data to not overfit, but get good quality predictions. And I'm just going to set, I think I might have made a mistake up here. I'm just going to copy in the levels so I don't have any problems. Okay, here we go. So by the way, if we wanted to just see the domain, we could do this. Okay, and now it's going to start training. And so if you put verbose equals 1, it will show you the results of each epoch, but I've just turned that off so we don't get too many things out in our output. As that runs in the background, I'm going to show you how, I'm just going to write out the code for evaluating this benchmark in the machine learning model that's underneath it. There's a really nice function called parity plot that's unique to the experimental emulator. And what that does is it shows a plot of measured values versus predicted, so you can get a sense of the fit. And we'll also just paste in some code here that does exactly what we did earlier, where we're able to get a sense of, does this predict anything? So we've got out this dictionary, which is probably a bit hard to interpret. So let's run this parity plot. So you can see, okay, it's getting a pretty good sense of the trend of the data, and we've got relatively good R squared between the measured and predicted and the test data set. So we feel comfortable that we can move on and use this as a benchmark. So if I do that, I see that I can predict for some conditions what the yield and turnover number is. So that's exactly what this allows us to do now, is that we have something that for any residence time, temperature, catalyst loading, and catalyst, we will be able to get a prediction of the yield and turnover number. So now we can plug this into our machinery with Summit and try to optimize, see how well different optimization strategies do at finding a maximum yield and turnover number. Okay, so in the last part, I'm going to quickly show you how we can use the experimental emulator as a benchmark in combination with any of the strategies to find optimal reaction conditions. And the way we'll do this is by doing exactly what we did above. So I'm actually just going to copy the code from what we had before, because it's exactly the same basically, except instead of using the SNAR benchmark, we're using the Suzuki benchmark. And so we can just plug it in here. And the only other change is that this multi to single objective transformation now has to have the correct variables. And since these are on the same scale, we can just add them directly. So let's try running this and see how it performs. And I'll let that run in the background and just make some notes as we close up about maybe what you might want to think about when you're trying to run these strategies. So earlier I went ahead and ran exactly the code above, but 20 different times, just to see the effect of randomness. You can see here some of the different Pareto plots. So here we're able to get pretty high yields and turnover numbers on this run. Here we got a bit lower turnover numbers, but still relatively high yields. And you can see us finding what we call the Pareto front, which is the set of trade-offs between maximizing yield and maximizing turnover number. Because as you increase yield, you have to increase the catalyst loading, which will decrease the turnover number. So there's a trade-off here. And So there's 20 of these. And what I also went ahead and did is there's a function in or strategy in Summit that is sort of classical full factorial design of experiments. So I just ran that, and you can see what that looks like here in terms of the yields and turnover numbers it found, or the conditions it found to give different yields and turnover numbers. And so what's often a challenge is you're trying to uh, compare different strategies, especially if it's multiple objectives. How do you compare them? And so one way is using the hypervolume. That's basically a measure of how well the strategy is finding the best trade-offs between your objectives. And so higher values are better. So basically what you do is see if you see this code, here you find the Pareto front. So in this case, it would be these 2 points. And you set a reference point. There's more in notes in the documentation on why you set this way. And then you can just calculate the hypervolume as a single scalar number. So here we can see that the hypervolumes are comparable, but here I had to run about 64 experiments for the full factorial. For the optimization, I was running 50, and I probably could decrease that even a bit more. So you can see that we're getting similar values with fewer experiments. If I just scroll back up here, I think now, yeah, it's done. And so it's gone and found our yield and turnover numbers and found sort of the Pareto front. And you can see here, this color bar represents the number of experiments. So red is very beginning, blue is sort of toward the end. And so you can see at the beginning, it's got some okay conditions. And then toward the end, it's really exploiting and finding the best conditions that maximize yield and turnover number. Okay. So I think we're going to finish just about there. And I'll just conclude by going over what we've talked about. In part one, I showed you how we can use strategies to optimize benchmarks. In particular, we looked at this nucleophilic aromatic substitution benchmark. And then we built our own benchmark based on experimental data. And finally, we optimized that and showed how we can use Summit to compare different strategies on the same benchmark. And so I hope this showed you that machine learning is really a powerful strategy for optimizing chemical reactions, from our initial guesses to what it's actually able to do. And after a couple rounds of experiments, is pretty impressive. And I hope that Summit really makes this accessible to everyone through a standard API for all different strategies, as well as being able to evaluate these strategies on benchmarks. And I'll finally note that we do use this in the lab. So we've got projects running this on flow chemistry equipment. And so, this is actually practically useful for optimizing reactions relatively quickly. So I'll stop there and say thank you for listening.